Presentation is devoted to giving some tips, some hints about some risk and rates of returns material. So just some ideas of pitfalls that I notice students tend to overlook or forget or misinterpret. Some ideas of some concept type questions that you're more likely to get than other things out of the text. So if you got a 70-page book chapter or whatever, I'd like to spend an hour or less maybe giving you some hints about things that would be really, really apropos to be prepared for in terms of evaluation, credit, that sort of thing. And of course, have a little bit of eye about finance in terms of like the sorts of things that are important sort of thing. So let's get moving here and talk about a few of those possibilities. So first, we ought to be conscious of the idea that when people talk about returns in finance, they're almost always talking about what we think of as a percentage return. Right now, a return on an investment is just a way of thinking of, well, how did I do? And it could be as simple as saying, well, my return was $4, right? I put in 3, I got back 7, that's $4. That's a dollar return, but that's really uncommon. A dollar return is not the typical way that people think of returns. In fact, it's so much so that in a finance world, when you're talking about anybody with a background in finance, and they say the word return, they're almost definitively talking about, well, how much did I make or lose on this investment? That's the numerator. And then they standardize or compare it to, well, what did it cost them to buy into this investment in the denominator, the price, right? So you have, in this case, a percentage return, either dividends received or interest received from a bond, from a loan sort of thing. Plus, did the value of it change? I bought it for 3, it went up to 7. Well, that's a $4 return, and I'd still have my 3 in the denominator. And did it pay any dividend or interest in the interim? Right, that gets tacked on as well. So the dividends and interest here would always be positive, right? And it's even called a dividend yield. You can actually think of this price as like something to distribute across this numerator. So instead of dividing by price, you could think of this as 1 over price times this numerator. Well, and then distribute so that your price in the denominator under dividends is your dividend yield. Or if you were talking about a bond and interest received, it would be your current yield is the term typically known. And then your market value, of course, can go up or down. That's your possibility of a capital gain or capital loss if it went down. So that's just talking about the change in the value of the asset if I was to go sell it today, right, versus what I paid for it. That part, of course, can be negative, unlike dividend or current yield. Right? It's known as my capital gain or loss. You combine all of that together and you have what's called a return. Now, our book likes percentage return sometimes with this sort of thing, but to me it's just return. And if you're talking about this with anybody finance-wise, you're going to be talking about returns. And you would never talk about a $7 return to a finance person. You'd only talk about a 7% return sort of thing. Of course, if you want this in percentage, you have to multiply by 100 because when this is spit out of this equation, it's going to be a decimal sort of thing. And so in this example, all right, $1,000 is invested, $1,100 is returned a year later. That's a 10% return. Right? If it also paid a $50 dividend, then you'd have 150 in the numerator because a dividend received of 50 would also get tacked into those parentheses. You have a 15% return, right? But this is a return. Right? A stock purchase for 50 pays a $2 dividend. Market value goes up to 54. Right? So you have a $4 capital gain. So it's 4 over 50 is the capital gain. 2 over 50 is the dividend yield. But you combine them all together, you have a $6 extra in your pocket after selling this 1 year later. So your overall gain is 6. That's the numerator divided by 50 is a 12% return. Right? But that's very, very commonly just called return alone. Now, when you have returns over multiple periods, then it's common to want to know, well, what sort of return have I tended to make on average sort of thing? There's 2 ways to consider that. One of them is the arithmetic mean. That's what you're most familiar with from school. And then there's the geometric mean, which you may or may not be as familiar with. So if you had 3 returns in subsequent years of 10, 20, and 30%, then The normal thing to do is just, well, those are my three values, add them up and divide by 3. Yeah, that's an average, but there's a more technical name for that average you've probably done your whole life. It's called the arithmetic average. Right? A special tool dealing with returns that recognizes the compounding nature of them is the geometric average, or geometric mean or average return. To do this, you have to put your returns in decimal form, right? So the 10% is 0.1, the 20% 0.2, the 30% 0.3. You add each of your decimal returns to 1. You multiply all of those sums together, and then you take the 1 over nth root. So if there were 3 observations here, you take the 1/3 power. Then you subtract 1. If you had a fourth return here of 40%, you'd also multiply this string by 1.4, and after doing those 4 pieces together to get a product, you take it to the 1/4 power before subtracting 1, sort of thing. And your geometric average is going to be lower, by the way, than your arithmetic average. The geometric mean is, usually we emphasize it with finance students via a really common example here that we have on the next slide, slide 6, right? The arithmetic average can be overly optimistic, especially when you're talking about over a long horizon sort of thing. Effectively, what it does is it overweights the importance of the good returns, right? If you make a 100% return in year 1 and a 50% negative return in year 2, what have you really made, right? Let's just take a value like, oh, I don't know, $30. To make a 100% return in 1 year means you multiply by 1 plus the return in decimal form. Well, 100% is just 1, right? So $30 grows to 60. Yeah, that's just a fancy way of saying that making a 100% return is the same as doubling your money in period 1. But what happens in period 2 when you lose 50%? Right? To lose 50% means you multiply by 1 plus negative 0.5. Of course, you don't have to work it out that formally with the arithmetic. Most of us understand a 50% loss just means you can cut it in half. I'm back to 30. Right, well, I started at 30 and I ended at 30, so it would be kind of crazy to say that my return was anything other than 0, right? My average return, right? If I start and end at the same spot, I didn't make any money. So 0 feels like it should be the output, and it is if you use our geometric average. With the arithmetic average, though, you're going to say my average return is 25%. That's crazy, right? Up 100 and down 50, though, right, is 100 minus 50 is 50 divided by 2 is 25. So yeah, you got to be careful with this sort of thing. And let's say in a lot of cases you'll be asked explicitly to do an arithmetic or geometric return. It's good to keep in mind the geometric mean is going to be smaller. Right? And if you're talking about the actual experience, the more realistic one, the geometric mean, is the way to go. Right? Risk is a possibility that more than one outcome can occur. If you have a locked-in guaranteed result, you have a risk of 0. And in fact, a lot of you are familiar with different measures of risk, things like standard deviation, and you actually can have a standard deviation of 0, and that's exactly akin to having no risk because you have a locked-in guarantee of exactly what will happen. There's different ways to measure risk, of course, but again, something like a standard deviation is probably the most commonly seen one out there. To me, I think the idea of risk is maybe best sort of kind of driven with a picture like this. The idea of risk, particularly in the real world and you're dealing with actual investors, right, is to keep in mind that people prefer, in this illustration, firm X to firm Y's returns. They both have a locked-in 15%, not a locked-in, excuse me, they both have an average return of 15%. That's our expected rate of return. But investors prefer X to Y, right? Why do they prefer X to Y? Well, long story short, investors are really, really fearful of this tail risk down here, right? Now, they're excited, of course, about the potential upside, right? This is a good thing. I'm trying to be gentle with my smiley face, right? The upside is good, but the downside is really bad, kind of thing. And the negative of this downside outweighs the positive of the symmetrical upside there when you're thinking about investment Y. Right? All right. So what would the ideal thing be to do? The ideal thing to do would be to keep an eye on shrinking the distribution of possible returns, trying to be more like X and less like Y with the eventual output of the sorts of returns I get, because I know that on the whole, if I can keep the expected return in the same area, I'm willing to trade off upside on the high for downside on the low. That's a fancy way of saying to get your standard deviation lower in this case. Most of us are familiar with this normal looking bell-shaped curve being based on a mean and standard deviation in a normal type distribution. Okay. Some real data here. This is one thing for your kind of your trivia area that you're probably going to want to keep in your hat, and for kind of concept questions and stuff like that, just knowing the order of this. In particular, that small cap stocks have done the best for 100 years plus ish now. Now, they're also the riskiest. They have by far the biggest standard deviation. They perform the best because with a small cap stock, if it becomes out of the gate and has some fantastic outcome, you have a lot of stocks in that kind of ballpark that can double or triple or quadruple or more in value. Whereas when you're dealing with large cap stocks, it's hard for them to grow that much that fast anymore. Okay. That's what takes the mean higher with small cap, but also the standard deviation a lot higher too, because you're also more likely to go bust and lose all of your investment inside of a small cap stock. Knowing the order of these returns, geometric or arithmetic, especially the first few, again, is a pretty good idea. That's a concept question tend to ask that small cap stocks the biggest, then larger cap stocks, and then longer term bonds sort of thing. Right? All right, so now what gets really interesting, as you might imagine, is there's lots of cases where you have potential trade-offs, right? Where you have one asset that has a higher expected return, right, but a much wider distribution. And you have something here with a much more definitive locked-in expected return, right, but less distribution. But this asset here has, the blue one, has no chance of a small gain or teeny gain or a loss, but it also has a much lower expected return, right, than this asset, kind of thing. So which do you prefer in this case? With the X and Y a minute ago, it was a very obvious choice for investors. But with this, different investors are going to feel differently about whether they prefer asset, say, K versus asset J. The blue or the black here is more of a matter of personal taste kind of thing and how much risk aversion a certain investor has. Right? Remember, if there's no risk, right, the standard deviation would be zero. Right? Whatever risk is actually a measure of how spread out or how distributed the potential things that could happen are. So if you have absolutely no risk, it's called risk-free. Right? Treasury bills, for example, are often held up as an effectively risk-free asset, and they are in terms of the cash that they pay back. They're not going to default. Right? They return their promise based on the economy, but there are still other kinds of risks. So T-bills, Treasury bills, the T, the capital T, stands for the Treasury Department of the United States, which is capitalized. Right? T-bills is the name for them. They're risk-free in terms of the payout that you're going to get. Oh, if I buy a $1,000 T-bill at 3%, I will make $30 next year plus my $1,000 back. That is risk-free, that part of the return. The value of what you're going to get at the end is not completely risk-free. It can vary. The value might be higher or lower based on inflation or other factors too. Right? So a little bit of thinking, a little bit of terminology. Effectively, though, we do often see the term risk-free rate applied to Treasury bills. Risk aversion, I mentioned the term a moment ago, right, is a name for disliking of risk. If you're averse to something, you dislike it. Right? So the more risk averse you are, the more likely you are to prefer something like my blue asset a minute ago, J, that's much more bunched, and avoid things like K, which might have a higher expected return, but also there's a lot more risk in them, which can again be measured by things like its standard deviation, etc. Knowing the term risk averse, risk aversion, right, is a good idea, good terminology thing to know. Risk-averse investors, therefore, to get them back to where they would take on risk requires a much bigger level of potential gain or expected return to compensate. Okay? We've talked about things kind of like the term required return a bit some, and thinking of like the required return on an investment, with an NPV of this or that. Well, we calculate the NPV based on a required return of 10% sort of thing, right? That's in a project setting. Well, in a setting like an investment, right, like a financial investment, a project is an investment too for a firm, but I'm talking about more of a traditional financial type of investment, maybe to visualize this best. The return that you expect or require is above and beyond the risk-free rate, right? And that amount above or beyond the risk-free rate is what's known as the asset risk premium. The idea is basically here that, well, every asset you'd invest in ought to return at least the risk-free rate, because people don't like risk. They're averse to it. So you ought to get the risk-free rate for free as an investor, right? But if I have an asset like asset, X, then we would often say like the premium, let me say, the asset S has required return of 9%. But if the risk-free rate is 3%, then the premium of asset X is 6%. The premium is just the amount above and beyond the risk-free rate. So much so that you often will even see the terminology written along the lines of like, hey, my premium is just my expected return above the risk-free rate, right? That computation right there is the premium on X's returns. So knowing the term premium and that it means an amount above and beyond the risk-free rate is a pretty nice little tool to have, or a little concept thing you'd want to be familiar with, right, as well. But we recognize investors make their decisions based on expected returns, and actual returns vary, right? In the long run, higher risk assets do indeed generally earn higher returns. There is a reason, but sometimes you need to go back 100 years to really see it. There is a reason that these things here with higher standard deviations have also had the highest expected returns, right? And goes in reverse towards lower expected returns. You are, over time, going to see the link between those two things. But in the short term, right, the higher standard deviation on something like small cap stocks can actually bury or crush you as an investor, because you can see the value go down more. And knowing about yourself or your clients and stuff like risk aversion becomes really useful in the real world, because if you're likely to jump ship, say, and sell out of an asset after you've lost a lot, and you have a high standard deviation on it, then it might not be something you can actually tolerate, and you might need to avoid things like that are too risky indeed. Required return and expected return are synonymous. An expected return and a required return are the same thing in finance. It's an expected return from the investor's point of view. It's the required return from sort of the security issuer or the firm's point of view. If I have a stock with a required return of 11%, the company that issued the stock thinks of that as more of a requirement. Oh, it's something that my owners are demanding of me. On the investment side, it's what I'd say I expect to make from this information. So the idea of expected return and required return being the same thing, that's kind of a nice little thing to know. In addition, right, again, I don't think this is not going to surprise you, but you would never have an expected return of an asset, practically speaking, that's negative or even less than your risk-free rate. Right? Now, of course, you see actual returns to investments that are negative all the time. Right? Bunches of stocks lose money every year, for example. So you might see an actual return of negative 3%. But whatever makes sense to have an expected return that's, say, negative, because no one would actually invest in anything when that's their expectation. Now, I can think of some real weird cockamamie examples to challenge that some, but that's basically the gist of it, sort of thing. Right? The amount of risk depends on how, if you are going to see a miss away from the expectation, how potentially large might that miss be, right? The difference between what could happen versus what's expected to happen is often tied really heavily to the idea of risk. You need to determine the return that's expected to start talking more about the risk. How do you measure return? Some people are fearful of Greek symbols. You really don't, it's not that hard to be. You think of an average, right? An average return, a mean return, an expected return. All those things are very equivalent in my mind. You know, the average return, expected return, mean return are all the same sorts of things. They're all just ways of saying, hey, all the things that could possibly happen, right? Weight those out there with returns and come up with an overall possibility. And the easiest way to do this really is with an example. So this is just giving you the math, the symbols behind a weighted average type of framework, where if it says, hey, if you want the expected or required return of an asset, just take every possible thing that can happen, right? Those are your Ks. I can make 2%. I can lose 8%. I can make 21%. Each possible thing that can happen, multiply it by the probability that it will happen. You're going to have a bunch of sums right then, products, of K times P. Add them all up. Add up those products. The sigma here, the sum sign means add up. That becomes your expected return. That reduces, by the way, to just taking the average, adding up all the P's and dividing by N if they're all equally likely. This reduces to like the same sort of average that you calculate in the 4th grade when they're all equally likely. They're not equally likely here. Here's 3 possibilities of what could happen next year. We would say things get better, things stay the same, things get worse. The most likely thing is that things stay the same, I have to give you these sorts of measures for now. They're economic forecast type things you can work on more later. But 50% is the most likely thing to happen, the highest probability. So when you're going to consider your returns, the same return of 12% happens if you have the same economy, say next year. That gets multiplied by the biggest probability, just 0.5. 12 times 0.5 is 6, and you see how this math works. The 3 products here in this baby example are then added together to get an expected return of 11%. Notice you never actually make 11% next year in this setup. You make either 22 or 12 or -8, right? That's one of the funny things about expected returns. Your expected return value might not match any of the individual things that really could happen. It's kind of a funny thing for people sometimes at first, right? The most common measure of standalone risk of all is standard deviation. I might have a concept question or two for you where I discuss coefficient of variation, which I'm going to show you in a couple slides. But by far the most common way of talking about standalone risk and measuring it is, well, how dispersed are my returns, right? And there are simpler measures of risk, right, that keep an eye on what could happen, right? The idea of risk, again, is kind of what could happen. Let's say 0. What if you have an asset that has, something like this distribution of expected returns, right? Well, you could talk about the risk. It might even go as low as -10 or as high as +30, but on average we expect to make about 6 or something like that. You could talk about the risk just in terms of the max and the min, right? The range here is 40, right? The range is just the high minus the low, right? But that pays no attention. The range is too simple, though, because it pays no attention to the difference between that illustration, right, versus that illustration versus that illustration. So the standard deviation pays more of a heed to the frequency of different sorts of things happening. It can be a bit scary to calculate by hand at first, right? This is the formula in symbols. It takes, for example, in this case, your 11 is the expected return that you need to find first. That's the K hat. You have to have the expected return before you can do the standard deviation. Then you take all of your possible outcomes, 22, 12, and -8. For each one of those, right, in this example, right, you subtract the 11, the 22, the 12, the -8. Right? That's what the terminology there means. You get new values, and you need to square them. 11 squared is 121, 1 squared is just 1, right? 19 squared is what, 361? I guess I should check that sort of thing, right? Whoops. Lost my cursor. Whoops, that's why. Yeah, it's 361. Weight each of these, multiply them again by their probabilities, 0.3, 0.5, 0.2. Add up those three sums, that's your variance. Take the square root of that variance, you have your standard deviation. Right? That's what that means in so many words. And then if you take the ratio of those two things, your standard deviation over your mean, that's called the coefficient of variation. It shows per unit of return how much risk do you have. Right? Now some concept things to be wary of, to be quizzed on and stuff, would be, hey, this is still a measure of standalone risk, as the slide notes, and that again, this is showing you per unit of return how much risk do you have. Right? Those are a couple of concept things that you'd want to be ready for. Right? Now, people kind of know what diversification tends to mean in a layman's sense, and you always hear the "don't put your eggs all in one basket" cliche sort of thing, and that's true, but the real reason you're doing it, if you never stop to really think under the hood of what's going on, is you're looking for things that behave differently at different times. Right? So the price is not always moving in the same direction. The real power of diversification is that you have some things that perform okay or even good in your portfolio, while other things don't. Because remember, investors are more scared of the bad than they are excited about the good. Right? So they're willing to give away some of the good if they can limit some of the bad. They're more scared about the bad than they are about the good. So they're willing to combine some assets that behave differently, because when they do so, right, they're getting the good part of this trade-off. They might even have the same expected rate of return, but they're shrinking the risk, and they're more fearful of this than they are this, which shouldn't be a surprise if you've studied some economics and utility and economics and stuff, right? People are really excited to win $100 if they're, poor college students, but somebody that's got, $1 million in the bank or so, they might not think twice one way or the other about winning $100 kind of thing. So if you're looking to diversify, it would be really nice to find things that behave differently at different times. The real goal of diversification simplifies down to finding things that behave differently from one another. And the more differently they behave, the more able you are to truly diversify. It'd be nice if there was a way to measure that sort of thing, and there is. It's called covariance. Right? Covariance is positive when things tend to move together. Right? If assets A and B have a positive covariance, that just means that their returns tend to go up together and down together. Right? This is a little bit tough for folks at first. A negative covariance doesn't mean that they both go down. A negative covariance means that they behave opposite one another. Right? If A tends to go up while B goes down, and B tends to go down while A goes up, or you get the idea, right? Then you have a negative covariance. So actually, a negative covariance is a really great thing if you're into investing, because those are the kind of assets that have a negative covariance that allow you to quickly attack that old Y distribution and get away from that potential loss in the left tail that everybody is so worried about. One hard thing about covariance, though, is the units can be really, really hard to identify. They're in kind of a squared unit framework, right? The units on covariance are the same as in variance. They're like squared return units, which is really hard to interpret. I mean, say you're talking percents for the sake of a little bit of ease. An 11% standard deviation is one thing, right? But 121 squared percent variance is really hard to wrap one's brain around, me included, right? So a really typical thing to do when talking about how assets move relative to one another is to standardize this relationship. So rather than talking about, hey, asset A and B have a covariance of 221 or negative 66 or whatever, a really typical thing to do is to standardize that covariance in the numerator here divided by the product of the standard deviation of A and the standard deviation of B. This is X here is a multiply sort of thing. So just take the standard deviation of A times the standard deviation of B in the denominator. That's why you kind of have squared units in the numerator divided by squared units in the denominator. And this thing is unitless. It doesn't have any, it's not in dollars, it's not in time, it's not in squared percents or nothing. It's just a naked number. And it ranges between -1 and +1. That's because the magnitude of sigma A times sigma B has to be larger than the magnitude of the covariance. That's just a kind of a fuzzy structural reality. Let's see. So the interpretation of that is a lot easier. -1 is the most negative covariance you can have. +1, the biggest, right, most positive. So let's talk about what that means. Maybe I think via an example is probably actually best, right? Here, right, this is an example of perfect positive correlation. Perfect positive correlation, you would think that has to be a good thing, right? Perfect positive correlation, right, just means that your correlation coefficient is +1. This is terrible. This isn't good. You don't want a perfect positive correlation. Why not? Well, look, what does it do for you? Nothing is the quick answer, right? Asset M, and then we call this M prime, right? They're just redundant. They both behave exactly the same. The blue and the red behave exactly the same. So when the colors match together, blue and red, and make purple, you haven't really diversified in any classical sense anyone would think. All you're getting is exactly the same kind of behavior for your money on your combined asset as you did on each of them individually. There's no diversification effect here. And this idea of perfect positive correlation providing no diversification effect and being a negative thing for most investors is something you want to be comfortable with conceptually. This is the best case. This is a perfect negative correlation, right? And it might have the word negative in it, but it's a good thing. A perfect negative correlation, right, is one with a correlation coefficient of -1, right? That takes you all the way from the old purple distribution past the red, and now you have a guaranteed locked-in return. Say it was 15% locked in would be pretty amazing, but this takes your risk down to nothing, as this flat purple line here, right, on the far right demonstrates. The 15% return is locked in, regardless of what either of your individual assets do. Get it? M and W are mirror images kind of thing. So when one is up, the other's perfectly down, that sort of thing. Right? That's the idea here. Perfect negative correlation allows you to eliminate all the risk. Now, this is an academic type concept. It's hard to find things that are negatively correlated at all, much less perfectly negative correlated. But you get the idea. And the good news about this is you don't need to find assets with negative correlations to get diversification benefit. You can even have, right, asset J and asset K and have a correlation coefficient of JK. This is how it's normally written, right, with their little subscript abbreviations there down to the side. You can have a correlation coefficient of like +0.5. And you still get a lot of diversification by buying both. Because if you have a J, right, it's going up and down like so, in a K, it might simultaneously be going up, but then it goes down some of those times. And it goes up while this is down, but down while this is up. But sometimes they go together, but sometimes they don't. But sometimes they don't, but sometimes they do. This kind of thing, if you have those kind of things simultaneously, then invariably, when you graph the picture together, it's still going to be smoother, right? It's still going to demonstrate less, right, risk than the individual components. So even having assets that are positively correlated together helps you some, as long as they're not perfectly positively correlated. And this is another illustration to show exactly that. You know, say you're talking about assets A and B. The green here in the blue, the correlations of perfectly negative, -1, and perfectly positive, +1, where you see these straight lines. Okay, those are the extreme cases. Again, hard to really ever see in reality, but right, if you have a perfect positive correlation, the best thing to do is just put all of your money in asset A if you hate risk, right? Or if you're willing to trade off some risk, you do asset B, but you're not getting diversification benefit, right? When you have perfect positive correlation. When you have perfect negative correlation, you can get the risk all the way down to 0 if you buy the right amounts of A and B relative to each other. Now, the detail on how to do so is a little much for this class kind of thing. That's some more advanced investment finance type stuff, but that's just the purple flat line on 15% for an example. You can get your return locked in with a risk. Remember, this is your risk here on the x-axis, all the way down to 0 with perfect negative correlation. But this example here, this one has correlation 0.2. The one I was just kind of making up on the spot was 0.5. Even with the correlation coefficient that's positive, you can actually get to levels of risk that are lower than either of your individual assets. That's surprising to people first, right? Asset A has this much risk. Asset B has this much risk. When I say risk, I'm measuring it on this axis, right? Yet, even though they're positively correlated, I can actually get my risk down a little bit by buying some of both. I can get my risk all the way down to here. That's a testament that diversification in some ways is easier than one might actually expect at first. Right? But the key is the assets, as long as they're not perfectly positively correlated, will provide some diversification benefit, and it'll just be more and more and more the lower and lower that your correlation, or covariance too, your correlation goes, kind of thing. Let's see, what else? Risk that only affects an individual asset is reduced when you hold assets in portfolios. If you get all assets, all company-specific risk could be eliminated, and you'll be left with market risk. Yeah, that's an illustration that we kind of continue here on the next slide, 27, and this slide, 28. Overall risk, the kind of risk we've been talking about, standalone overall, is 11%, 18%, 27%, is a combination of two things. Some risk is specific to the asset that you're talking about, company-specific risk. It gets other names too, like diversifiable risk, right? Firm-specific risk, company-specific risk. The idea here is it generates from having company-specific problems, issues, things. They're not always bad. They could be things like a breakthrough on a new product, but they're typically, we think about the bad things like getting in trouble with the IRS or having a strike or being the loser in a lawsuit or things like that, right? But you're not going to lose that much money if you can diversify across everything. On the flip side, if you have a lot of money in one company and they lose a lawsuit, that's exposing you to a lot more risk. Other kinds of risk are not tied uniquely to one company. They're market-wide. In fact, when the stock market goes up, say 1% in a day, it's not usually that one company out there, Coca-Cola, went up 80% and everything else stood flat. No, what usually happens is everybody went up. There's usually some external underlying thing that's affecting everything simultaneously. It's a concept question here, the difference between company-specific and market risk, that you really do want to be ready for, sort of thing. You can diversify away from company-specific risk, right? Just by buying more and more assets, even randomly held assets. Say you split your money into 100 different things with 1% in each, or 500 different things with 0.2% in each. As you diversify more and more and more amongst different things, you're getting away from company-specific risk. Right? You can get it all the way down to nothing. This illustration here on our slide right here shows you that after about 30 or 40 stocks, you've eliminated effectively all of your standalone risk. Right? That's a concept thing I'd be ready for as well. You still have risk to investing, but it's the risk that permeates everything. Your shares in all 100 companies that you own. There can be things like government-specific issues and war and recessions and stuff that affect all companies across the board, right? And in that case, the market risk would play against you. Or you can have hot economies, right? Good consumer confidence, things like that can help everyone simultaneously and have market risk pay off sort of thing as well. But you can diversify away company-specific risk, not the market risk, and the two combined together becomes your overall risk. Right? The comment here in your slide, kind of another formal way of stating this. Expected returns are linear, right? But standard deviations are not linear, and that's a good thing. That's a good thing. This is why you can lower your risk, and again, this is a really powerful thing. You can buy some A and B together and actually get a risk that's lower than the risk of either one, right? That's surprising to people. People tend to assume that everything is linear, right? People get their head around pretty quickly that if you have two assets, right, like we'll call them element P and Q, right? And if my expected return on P, I'm going to put half the money in each, right? And if my expected return on P is 10% and my expected return on Q is 14%, right? Then if I buy a 50-50 P and Q, my expected return is indeed 12%. That's true. That's correct. But standard deviation doesn't work that way. You can have a standard deviation of P that's 20%, standard deviation of Q that's 30%, and people presume that if you buy both of them, right, standard deviation of P and Q, that it has to be in the middle again, 25. No, that's not how it works. It just totally depends on how they co-vary or correlate with each other. But you actually can get cases where you can get the risk down to an even lower level, right? Even than either one of them, excuse me. And when you do that and diversify, you're getting a higher trade-off in terms of expected return, or at least an even trade-off in terms of expected return, I should say. But you're dumping more and more risk with diversification, kind of thing. This culminates in some of the most interesting parts, and can be challenging too, parts of investment finance, where the reality is investors are actually pretty well served to order something or to pick something what we call on the efficient frontier. Right? The efficient frontier is actually the optimal set of different things of investments that people should consider buying. Right? So a lot more detail out there if you're looking for it, particularly even in our text and such like that too. But this piece, right, this shape, this kind of curved looking thing that opens down and flattens out like this is your efficient frontier. Right? That's the name for this thing. It compares the risk on the x-axis to expected return on the y-axis of a portfolio, hence the little subscript P. Right? And the idea being that there's no reason to ever settle for anything with an expected return standard deviation like that. Why would you ever do that? If you're going to take this much risk, you ought to get more expected return. Or you ought to take that much expected return and get less risk. Right? But don't buy this spot, don't buy this point, or this one, 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 or any of those either. The only things that an investor would consider, originally at least, is these things on this efficient frontier. And then we can take this concept to the next level too and say, oh, this actually improves even more if you add a risk-free asset, right, into the mix. And we'd say that the risk-free asset, and we'd say this is getting a little heavy, but a risk-free asset might return something like, right, 1 or 2 or 3% or 4 or 5, whatever you want, but it has zero risk. That's what makes it risk-free, right? And the capital market line here is the name for the line, right, that's tangent to the efficient frontier. That means it hits it and intersects it in only one point if it's been a while for you in the geometry realm. And what this actually reduces to is that every investor is supposed to buy some combination of this specific spot right here, which is called the market portfolio, and this risk-free rate down here. Right? And you buy 100% market portfolio and 0% risk-free rate, or down here you could have 0 market portfolio and 100% risk-free rate, or you could buy 50-50, or you could borrow at the risk-free rate and buy 120% premium or market portfolio, excuse me, and negative 20 risk rate. Those are all the possibilities in investment finance that we'd say investors should be interested in. It's not always exactly that simple, right? But that's a big part of the gist of there. All right, we're going to kind of work backwards a little bit here and talk about portfolio return in a different light a bit. As a segue, the idea that are you compensated? People always say more risk, more reward, more risk, more return, that sort of thing. And that's sort of true, but it's not quite that routine or simple. So the idea of more risk, more return is a bit overstated. Okay? You can take on more risk by taking on more firm-specific risk, right? But that's not the kind of risk that is compensated typically. It's just that you have more huge wins and huge losses when you take on more firm-specific risks. But your expected return, right, how much you project to make, that's not higher just because you have more risk. All right, let's talk about moving some pieces around to sort of demonstrate that kind of thing. Right? What if I have a portfolio with different weights? W stands for weights. There's the fractions, right, invested in different pieces. And each one of those investments is in for an asset I. So in this abbreviation here, this summation thing, I have assets maybe say 1, 2, 3, 4. We'll go triple A through triple D, triple A, B, C, D. Those are 4 assets. I'm going to buy different amounts of the 4, right? And then they each have their own, right, returns or expected returns. If I want to get a portfolio expected return, I just weight each of the K's, each of the return amounts, by how much money relatively is in each one. So the W's here, the W's add up to 1. Right? You add up the sum of all of the W's, right? The amounts invested, right, in the denominator, that makes the denominator. And then each of the individual amounts invested, right, is in the numerator. Right? I guess total dollars, right? Asset I kind of thing. Easiest really to see via example. Like looking at this one, you have $20,000 invested. Right? The grand total invested here is $20,000. Right? Well, 10% of it's in AAA, 20% here, 30% here, 40% here. Right? So if I want to know my expected return of these, all I literally do is multiply these weights. These are all the W's here in my column. They must add up to 1, 0.1, 0.2, 0.3, 0.4, summed is 1, right? Multiply, right, by each of these, and the grand total of what you get when you multiply in this case is 15.3%. Right? That's the expected return of this portfolio, 15.3%. Let's talk about a different kind of risk measure here and sort of pivot a bit more. If standalone risk is measured by standard deviation, right, but we just mentioned a couple of slides back that having more firm-specific risk doesn't compensate you with a higher return, right? Well, that means something has to give, right? So if you have your standalone risk or your sigma risk is a combination of your firm-specific, right, plus your systematic, right? But your firm-specific risk is not compensated. So you're not compensated for taking any more of it on, right? It would really be nice to know a way to measure your systematic risk, right? Because ultimately, right, it's not that you have more risk, right? It's not higher standalone risk, higher portfolio or asset return. No, that's not true. But it is true that the higher amount of systematic risk you take on, the higher your portfolio return tends to be. That is true. We want to measure this systematic risk. Is there a way to measure it? There is. Right? It's measured with a quantity, right, called beta. Right? You'll see the word beta. You'll see a little lowercase b sometimes. You'll see sort of the Greek beta oftentimes as a measure for it. Beta is actually the ratio of the covariance of an asset with the market. Notice the little I subscript here is, say, for an asset I, its beta is relative to how it covaries with the market. Km is the return on the overall market. What market? Right? This market back here that we were talking about buying, the market portfolio that combines your frontier and the risk-free rate. Right? And then how does that compare, right, to the variance of market returns? Right? Unlike your correlation coefficient, this actually can be larger than 1, right? Because this time you're dealing with a different quantity in the denominator. This is still an x. This is still squared. It's your market return variance squared. This is another expression for it too. It's your correlation of the asset with the market multiplied by this ratio. Right? The beta measures what's going to happen, right, to an asset's return when the market return changes. It's basically a measure of how elastic you are or how sensitive you are. Right? So I'm even going to kind of write that out. Right? Beta, like beta. How sensitive are you to market returns? Right? A beta of 1 is standard. It means that you move 100% as much as the market. Right? So you move 100% as much as the market. It's just the typical level. Beta of 1 is standard. It's the same overall risk as the market. A beta bigger than 1 is riskier than the market. It's more sensitive. It demonstrates an asset that whose returns move more than the market. Beta less than 1 works in reverse. I think a picture, right, can help demonstrate that one too. Right? If this here will say over time is your market return, right, then this asset right here that goes up harder, right, and down harder, up harder and down harder, up harder. This might have say a beta, and we'll call this asset X, right? And we'll say that the beta of X might be something like 1.7. Right? Here's a different asset. It goes, it goes up less, right, but then also down less, and up less, but also down less. It's less sensitive to how the market moves. You might call this asset Y, and the beta on asset Y might be something like 0.7. You know, 1 is the standard, kind of matches along with the black line. Things that are bouncier, right, have higher betas than 1. Things less bouncy, betas lower than 1. Right? And the idea is, okay, what does this mean, that high betas are good? No, they're just more dangerous. Are low betas bad? No, they're just safer, sort of thing. If you're in a situation now where the market instead goes, next period, say the market goes down instead, well, your beta here is going to go down less. Right? And this beta here is going to go down more. And the flip's true in a period where the asset returns positive. And how do you actually measure the beta? You can use this formula back here, but the most direct way to do it is just to regress the returns of your asset, right? Let that be the Y variable. Regress that on the market returns. Right? This can be a challenge to do. You have to find things to proxy for, like how far back do we go? Do we go back months? Do we go back years? How frequently do we measure these returns and things like that? But generally speaking, if you wanted to get the beta, right, for asset X, you do the returns on asset X, compare those to the returns on the market, right? And you just graph the comparison, right, over time, right? They both go up together or down together. Right? And if you have a typical level of beta, right, you might have a beta of about 1. Right? But if you have another asset who goes way up even when the market just goes up a little, but goes way down, right, even when the market's just down a little, this has a beta that's way bigger. It's way more sensitive. And this one here, right, whoops, is way less sensitive. Right? This might have a beta of 0.4, sort of thing. Okay? The market drives a lot of returns, right? A lot of things go up and down together. Okay? So a big surprise for people, or a scary thing, or a weird thing, I guess I should say, for people, is that market risk is a huge part of risk. Market risk is a big factor. And investors don't tend to like it, right? So the more market risk, the more exposure you have to the market, the higher your beta. Right? When you have more market exposure or risk, the higher your beta. Right? Well, what does that mean? Well, going back to the more market risk thing at least, it means like investors are fearful. Investors are concerned or fearful or scared. Right? That drives the price of asset X down. Right? And when the price goes down for something and you can buy it cheaply, that makes the expected return on the asset go up. Right? If you can buy it cheap, it makes the expected return higher. So you effectively end up having a link here where the higher your beta, the higher your expected return on an asset. Right? And that's true. It's done in finance with this model known as the capital asset pricing model. It basically says the higher your beta, the higher expected return you project. The return on any asset in words is equal to the risk-free rate, remember, for any investment should be an automatic, plus the beta times your risk premium above the market portfolio. Right? Of the market portfolio, over the risk-free rate. This is a really common equation in finance. It's the CAPM, the capital asset pricing model, or CAPM for short. It demonstrates a link between risk and return. Right? Notice the only the asset here that's specific is I, and the only other time you see the abbreviation I is on the beta. So if you're talking about the return for, say, Coca-Cola, and you want to talk about the return of Coca-Cola, you'd use the risk-free rate, the market return, and the risk-free rate again. The only thing that would be beta specific would be a beta for Coca-Cola. And if you had a different risk profile on Apple, right, there's nothing Apple specific on the other side of this equation, right, except for the beta of Apple. So the beta as taken from that regression or otherwise becomes a really big part of determining the expected return for an asset. Now, it becomes a really quick arithmetic thing to do if the information is just given to you, like it here is in this slide. 4% risk-free rate, market return of 10, beta of 1.5 is a 13%, right, expected return for your asset. Literally just plug the pieces in. 4 plus 6 times 1.5, order of operations, do the multiplication first. 9 plus 4 is 13. Right? Again, be careful with the word premium. You'll sometimes see, instead of seeing a market return quoted, sometimes you'll be told that the market premium or risk premium is 6. That's the same information. It's just if you're told the premium, you're being told this quantity here all at once. So you got to be careful with vocabulary in how you discuss that sort of thing. Okay? I think I have one concept question potentially around saying that the slope of the security market line is your premium, because security market line compares your beta, right, on your x-axis with the expected return on the y-axis. Well, we know the expected return is direct function of beta, with the risk-free rate as the intercept, right, and the beta is the slope. Right? Well, you flip it on its head now, and hey, the higher your beta gets, then the higher expected return. That's the security market line, and the slope now in this case is the premium. Right? Betas are weightable, so if you have multiple assets, like in this next example where the betas are 3, 2.5, 1.6, 1.2, you could do the same weighting type scheme that we did before. You can say, oh, well, the grand total here is 20,000, so this is 10%, 20%, 30%, 40%, and you can multiply yet again and add them all up, and betas behave just like expected returns do. Right? They're linear again, to use the word. This is a really high beta, by the way, 1.76. If you were to apply it with the same specs here of a 13% market return and a 5% risk-free rate, you're getting a really high portfolio expected return of 19.08%. This CAPM is, the concept is really good. Right? It definitely demonstrates a reality that the link is between market risk and expected return is a valid one, that firm-specific risk is less valid, right? And that these things hold up over time. Right? But there's always problems with this sort of thing. For one thing, it's a really simple model. It's really only based on one factor, this beta, and research has showed us some other things might matter too. Using historical data to talk about the covariance or correlation of something with the market, that isn't necessarily always true, right, going forward. Let's think. So we've done a lot here, right? Long section, but trying to give some hints and ideas along with the practice items and materials and book that you have available, some things to highlight. So hopefully adding some value, as always. Okay, rates are basic goal. Maximize shareholder wealth. Right? Okay, signing off.